guys, we're studying with me. Hello.
One, I'll check that off. We have a 5, I'll check that off. We get a 6, I'll check that off. Well, the next box, we got another 6. We already have that prize. We're gonna keep getting boxes. Then the next box, we get a 2. Then the next box, we get a 4. Then the next box, the number's a 7. So we will just ignore this right over here. The box after that, we get a 6. We already have that prize. Then we ignore the next box, a 0. That doesn't give us a prize. We assume that didn't even happen. And then we would go to the number 3, which is the last prize that we need. So how many boxes did we have to go through? Well, we would only count the valid ones, the ones that gave a valid prize between the numbers 1 through 6, including 1 and 6. So let's see, we went through 1, 2, 3, 4, 5, 6, 7, 8 boxes in the first experiment. So experiment number 1, it took us 8 boxes to get all 6 prizes. Let's do another experiment, because this doesn't tell us that on average she would expect 8 boxes. This just meant that on this first experiment it took 8 boxes. If you want to figure out on average, you want to do many experiments. And the more experiments you do, the better that average is going to, the more likely that your average is going to predict what it actually takes on average to get all 6 prizes. So now let's do our second experiment. And remember, it's important that these are truly random numbers. And so we will now start at the first valid number. So we have a 2. So this is our second experiment. We got a 2. We got a 1. We can ignore this 8. Then we get a 2 again. We already have that prize. Ignore the 9. 5, that's a prize we need in this experiment. 9, we can ignore. And then 4, haven't gotten that prize yet in this experiment. 3, haven't gotten that prize yet in this experiment. 1, we already got that prize. 3, we already got that prize. 3, already got that prize. 2, already got those prizes. 0, we already got all of these prizes over here. We can ignore the 0, already got that prize. And finally, we get prize number 6. So how many boxes did we need in that second experiment? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 boxes. So in experiment 2, I needed 17, or Amanda needed 17 boxes. And she can keep going. Let's do this one more time. This is strangely fun. So experiment 3. Remember, we only want to look at the valid numbers. We'll ignore the invalid numbers, the ones that don't give us a valid prize number. So 4, we get that prize. These are all invalid. In fact, and then we go to 5, we get that prize. 5, we already have it. We get the 2 prize. 7 and 8 are invalid. 7's invalid. 6, we get that prize. 7's invalid. 1, we got that prize. 1, we already got it. 9's invalid. 2, we already got it. 9 is invalid. 1, we already got the 1 prize. And then finally, we get prize number 3, which was the missing prize. So how many boxes, valid boxes, do we have to go through? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So it's only 3 experiments. What was our average? Well, with these 3 experiments, our average is going to be 8 plus 17 plus 10 over 3. So let's see. This is 25, 35 over 3, which is equal to 11 and 2/3. Now, do we know that this is the true theoretical expected number of boxes that you would need to get? No, we don't know that. But the more experiments we run, the closer our averages likely get to the true theoretical average. Pascal Ricketts has invented a game called 3 rolls to 10. You roll a fair 6-sided die 3 times. If the sum of the rolls is 10 or greater, you win. If it is less than 10, you lose. What is the probability of winning 3 rolls to 10? So there are several ways that you can approach this. The way we're going to tackle it in this video is we're going to try to come up with an experimental probability. We're going to do many experiments trying to win 3 rolls to 10 and figure out the proportion that we actually win. And the more experiments we try, the better, the more likely that we're going to get a good approximation of the actual probability. So let's do that. And to help us, I'm going to have a computer generate a string of random digits from 0 to 9. And the way that we're going to use this is, remember, we're rolling a fair 6-sided die. So the outcome could be 1, 2, 3, 4, 5, or 6 for each roll. In this random number list that the computer has generated, I do get digits from 1 to 6, but I also get the digits 7, 8, 9, and 0. And so what I'm going to do for each experiment, I'm going to start at the top left, and I'm going to consider each digit a roll. If it gives me an invalid result for a 6-sided die, so if it's a 0, an 8, a 7, or a 9, I will just ignore that. I will just say, well, that wasn't a valid roll. It's like you roll the die and it fell off the table or something like that. So let's do that. Let's do multiple experiments of taking 3 rolls, sum them up, and we'll see how many we can do to figure out an experimental probability of winning Pascal's game. So let me set up a little table here. So I want space to show the sum. So this is going to be the experiment. So let me write the sum. And over here, we're going to say, did we win? All right. So let's start with experiment 1. So our first roll, we got a 1. Our second roll, we got a 5. We're doing quite well. And then our third roll, we got a 6. Did we win? Well, 1 plus 5 plus 6 is 12. Yes, we won. Let's do another experiment. This is going to be experiment 2. We'll just keep going here. These are random digits. So we have a 6 in our first roll. We got a 2 in our second roll. We got a 4 in our third roll. Did we win? Yes. Once again, this summed up to 12. So we won. All right, let's do another experiment. So experiment number 3. So this first thing is invalid. So this is our first roll. We got a 6. And then this is invalid. Our second roll, we get a 3. This is invalid. That is invalid. That is invalid. And then in our third roll, we got a 2. So we squeaked by. This adds up to 11. Yes, that looks like a win. All right, let's do our fourth experiment here. So our first roll, we got a 1. This is invalid. Second roll, we got a 2. This is invalid. Third roll, we get a 5. Did we win? 1 plus 2 plus 5 is 8. No, we did not win. So that's our first non-win. So let's keep going. This is interesting. All right, this is invalid. So we're going to have, so this is trial 5. We're going to have 4 plus 3 plus 1. 4 plus 3 plus 1 adds up to 8. Did we win? No. Let's just keep going here. So I'm going to keep going with my table where I have experiment. I'll do 5 more trials. Experiment, sum, and do we win? Let me make the table. This is just a continuation of the table we had before. I don't want to go below the page because I want to be able to look at our random numbers here. So we are on to experiment 6. Experiment 6, we are getting a 3 in the first roll, a 3 in the second roll. This isn't looking good. And then a 2 in our third roll. Did we win? No. This is less than 10. Now we go to experiment 7. Experiment 7. We get a 2 in our first roll. This is invalid. We get a 3 in our second roll, plus 3. And we get a 1 in our third roll. So plus 1. Once again, we did not win. Now we go to experiment. We will go to experiment 8. We get a 1 in our first roll. We get a 3 in our second roll. This is invalid. The die fell off the table. We can think of it that way. And then in our third roll, we get a 5 plus 5. Did we win? No, this adds up to 9. So we had a string of wins to begin with, but now we're getting a string of non-wins. All right, now let's go to experiment 9. So we get a 6 in our first roll. We get a 4 in our second roll. And then these are all invalid. And then we get a 5 in our third roll. Did we win here? Yes, we won over here. This is definitely going to be greater than 10. This is 15 here. All right, last experiment, or at least for this video, last experiment. You could keep going. In fact, I encourage you to after this. See if you can get a more accurate, a better approximation of the theoretical probability of winning by doing more experiments to calculate an experimental probability. So here, experiment 10. First roll, we get a 5. Second roll, we get a 2. This is invalid, invalid, invalid. Then we get a 6. Here, we definitely won. So with 10 trials, based on 10 trials or 10 experiments, what is our experimental probability of winning this game? Well, out of the 10 experiments, how many did we win? it looks like we won 1, 2, 3, 4, 5. So based on just these 10 experiments, we got a pretty clean 50%. So do you think the theoretical probability is actually 50%? Maybe you want to continue running these experiments over and over. Maybe we want to do a computer program that could run this experiment instead of 10 times, maybe 10,000 times, to see if we can get closer to the true theoretical probability. Let's do a little bit of probability cards. And for the sake of this video, we're going to assume that our deck has no jokers in it. You could do the same problems with a joker. You'll just get slightly different numbers. So with that out of the way, let's first just think about how many cards we have in a standard playing deck. So you have 4 suits. And the suits are the spades, the diamonds, the clubs, and the hearts. You have 4 suits. And then in each of those suits, you have 13 different types of cards, or sometimes it's called the rank. So each suit has 13 types of cards. You have the ace, then you have the 2, the 3, the 4, the 5, the 6, 7, 8, 9, 10, and then you have the jack, the king, and the queen. And that is 13 cards. So you can have, for each suit, you can have any of these. For any of these, you can have any of the suits. So you can have a jack of diamonds, a jack of clubs, a jack of spades, or a jack of hearts. So if you just multiply these two things, you could take a deck of playing cards and actually count them, take out the jokers and count them. But if you just multiply this, you have 4 suits. Each of those suits have 13 types. So you're going to have 4 times 13 cards, or you're going to have 52 cards in a standard playing deck. Another way to say it is like, look, there's 13 of these ranks or types, and each of those come in 4 different suits. 13 times 4, once again, you've gotten 52 cards. Now with that out of the way, let's think about the probabilities of different events. Let's say I shuffle that deck, I shuffle it really, really well, and then I randomly pick a card from that deck, and I want to think about what is the probability that I pick a jack. Well, how many equally likely events are there? Well, I could pick any one of those 52 cards. So there's 52 possibilities for when I pick that card. And how many of those 52 possibilities are jacks? Well, you have the jack of spades, the jack of diamonds, the jack of clubs, and the jack of hearts. There's 4 jacks. There's 4 jacks in that deck. So it is 4 over 52. These are both divisible by 4. 4 divided by 4 is 1. 52 divided by 4 is 13. Now let's think about the probability. So we're going to start over. I'm going to put that jack back in. I'm going to reshuffle the deck. So once again, I still have 52 cards. So what's the probability that I get a hearts? What's the probability that I just randomly pick a card from a shuffle deck and it is a heart? Its suit is a heart. Well, once again, there's 52 possible cards I could pick from, 52 possible equally likely events that we're dealing with. And how many of those are hearts? Well, essentially 13 of them are hearts. For each of those suits, you have 13 types. So there are 13 hearts in that deck. There are 13 diamonds in that deck. There are 13 spades in that deck. There are 13 clubs in that deck. So there are 13 of the 52 would result in hearts. And both of these are divisible by 13. This is the same thing as 1/4. 1 in 4 times, I will pick it out, or I have a 1 in 4 probability of getting a hearts when I go to that, when I randomly pick a card from that shuffle deck. Now let's do something that's a little bit more interesting, or maybe it's a little obvious. What's the probability that I pick something that is a jack? I'll just write J. It's a jack and it is a hearts. It is a jack and it is a hearts. Well, if you're reasonably familiar with cards, you'll know that there's actually only one card that is both a jack and a heart. It is literally the jack of hearts. So we're saying, what is the probability that we pick the exact card, the jack of hearts? Well, there's only one card that meets this criteria right over here, and there's 52 possible cards. There are 52 cards. I shuffle it, randomly pick a card. There are 52 possibilities. There are 52 possibilities. But how many of those possibilities meet the criteria, meet these conditions that it is a jack or a heart? And to understand that, I'll draw a Venn diagram. Sounds kind of fancy, but nothing fancy here. So imagine that this rectangle I'm drawing here represents all of the outcomes. So if you want, you can imagine it has an area of 52. So this is 52 possible outcomes. Now, how many of those outcomes result in a jack? So we already learned this. 1 out of 13 of those outcomes result in a jack. So I could draw a little circle here where that area, and I'm approximating, that represents the probability of a jack. So it should be roughly 1/13 or 4/52 of this area right over here. So I'll just draw it like this. So this right over here is the probability of a jack. The probability of the jack. It is 4. There's 4 possible cards out of the 52. So that is 4/52 or 1 out of 13. 1/13. Now, what's the probability of getting a heart? Well, I'll draw another little circle here that represents that. 13 out of 52. 13 out of these 52 cards represent a heart. And actually, one of them represents both a heart and a jack. So I'm actually going to overlap them, and hopefully this will make sense in a second. So there's actually 13 cards that are a heart. So this is the number of hearts. Number of hearts. And actually, let me write this top thing that way as well. It makes it a little bit clearer that we're actually looking at. So clear that. So the number of jacks. And of course, this overlap right here is the number of jacks and hearts. The number of items out of this 52 that are both a jack and a heart. It is in both sets here. It is in this green circle and it is in this orange circle. So this right over here, I'm doing that in yellow since I did that problem in yellow. This right over here is the number of jacks and hearts. So let me draw a little arrow there. It's getting a little cluttered. Maybe I should draw a little bit bigger. Number of jacks and hearts. Number of jacks and hearts. And that's an overlap over there. So what is the probability of getting a jack or a heart? So if you think about it, the probability is going to be the number of events that meet these conditions over the total number of events. We already know the total number of events are 52, but how many meet these conditions? So it's going to be the number, you could say, well, look, the green circle right there says the number that gives us a jack, and the orange circle tells us that the number that gives us a heart. So you might want to say, well, why don't we add up the green and the orange? But if you did that, you would be double counting. Because if you just did 4, plus 13, what are we saying? We're saying that there are 4 jacks, and we are saying that there are 13 hearts. But in both of these, when we do it this way, in both cases, we are counting the jack of hearts. We're putting the jack of hearts here, and we're putting the jack of hearts here. So we're counting the jack of hearts twice, even though there's only one card there. So you have to subtract out where they're common. You have to subtract out the item that is both a jack and a heart. So you would subtract out a 1. Another way to think about it is, you really want to figure out the total area here. You want to figure out this total area. Let me zoom in, and I'll generalize a little bit. So if you have one circle like that, and then you have another overlapping circle like that, and you wanted to figure out the total area of both of the circles combined, you look at the area of this circle. You would look at the area of this circle, and then you could add it to the area of this circle. But when you do that, you'll see that when you add the 2 areas, you're counting this area twice. So in order to only count that area once, you have to subtract that area from the sum. So if this area has A, this area is B, and the intersection where they overlap is C, the combined area is going to be A plus B minus where they overlap, minus C. So that's the same thing over here. We're counting all the jacks, and that includes the jack of hearts. We're counting all the hearts, and that includes the jack of hearts. So we counted the jack of hearts twice, so we have to subtract 1 out of that. So it's going to be 4 plus 13 minus 1, or this is going to be 16/52, and both of these things are divisible by 4. So this is going to be the same thing as divide 16 by 4, you get 4. 52 divided by 4 is 13. So there's a 4/13 chance that you get a jack or a hearts. Let's say I have a bag, and in that bag, I'm going to put some green cubes in that bag. And in particular, I'm going to put 8 green cubes. I'm also going to put some spheres in that bag. Let's say I'm going to put 9 spheres, and these are the green spheres. I'm also going to put some yellow cubes in that bag. Some yellow cubes. I'm going to put 5 of those, and I'm also going to put some yellow spheres in this bag. Yellow spheres. And let's say I put 7 of those. I'm going to stick them all in this bag, and I'm going to shake that bag, and I'm going to pour it out, and I'm going to look at the first object that falls out of that bag. And what I want to think about in this video is what are the probabilities of getting different types of objects. So for example, what is the probability? What is the probability of getting a cube? A cube of any color. What is the probability of getting a cube? Well, to think about that, we should think about or this is one way to think about it. What are all of the equally likely possibilities that might pop out of the bag? Well, we have 8 plus 9 is 17. 17 plus 5 is 22. 22 plus 7 is 29. So we have 29 objects. There are 29 objects in the bag. Did I do that right? This is 14. Yep, 29 objects. So let's draw all of the possible objects. I'll represent it as this big area. I'll represent it as this big area right over here. So these are all the possible objects. There are 29 possible objects. So there's 29 equal possibilities for the outcome of my experiment of seeing what pops out of the bag, assuming that it's equally likely for a cube or sphere to pop out first. And how many of them meet our constraint of being a cube? Well, I have 8 green cubes and I have 5 yellow cubes. So there are a total of 13 cubes. So let me draw that set of cubes. So there's 13 cubes. I can draw it like this. There are 13 cubes. This right here is the set of cubes. This area, and I'm not drawing it exact, I'm approximating, represents the set of all the cubes. So the probability of getting a cube is the number of events that meet our criterion. So there's 13 possible cubes that have an equal likely chance of popping out over all of the possible equally likely events, which are 29. That includes the cubes and the spheres. Now let's ask a different question. What is the probability of getting a yellow object, either a cube or a sphere? So once again, how many things meet our conditions here? Well, we have 5 plus 7. There's 12 yellow objects in the bag. So we have 29 equally likely possibilities. I'll do that same color. We have 29 equally likely possibilities, and of those, 12 meet our criteria. So let's say, let me draw 12 right over here. Do my best attempt. So let's say it looks something like, so the set of yellow objects, they're 12 objects that are yellow. So the 12 that meet our conditions are 12 over all the possibilities, 29. So probability of getting a cube, 13 29s, probability of getting a yellow, 12 29s. Now let's ask something a little bit more interesting. What is the probability of getting a yellow cube? So I'll put it in yellow. So we care about the color now. So this thing is yellow. What is the probability of, or as my son would say, lello. What is the probability of getting a yellow cube? Well, there's 29 equally likely possibilities. And of those 29 equally likely possibilities, 5 of those are yellow cubes or lello cubes. 5 of them. So the probability is 5 29s. And where would we see that on this Venn diagram that I've drawn? This Venn diagram is just a way to visualize the different probabilities. And they become interesting when you start thinking about where sets overlap or even where they don't overlap. So here we're thinking about things that are members of the set yellow. So they're in this set and they are cubes. So this area right over here, that's the overlap of these two sets. So this area right over here, this represents things that are both yellow and cubes because they're inside both circles. So this right over here, let me write it right over here. So there's 5 objects that are both yellow, and cubes. Now let's ask, and this is probably the most interesting thing to ask, what is the probability of getting something that is yellow or a cube of any color? Probability of getting something that is yellow or a cube of any color. Well, we still know that the denominator here is going to be 29. These are all of the equally likely possibilities that might jump out of the bag. But what are the possibilities that meet our conditions? Well, one way to think about it is, well, probably there's 12 things that would meet the yellow condition. So that would be this entire circle right over here. 12 things that meet the yellow condition. So this right over here is 12. This is the number of yellow. That is 12. And then to that, we can't just add the number of cubes because if we add the number of cubes, we've already counted these 5. These 5 are counted as part of this 12. One way to think about it is there are 7 yellow objects that are not cubes. Those are the spheres. There are 5 yellow objects that are cubes. And then there are 8 cubes that are not yellow. That's one way to think about it. So when we counted this 12, the number of yellow, we counted all of this. So we can't just add the number of cubes to it because then we would count this middle part again. So then we have to essentially count cubes, the number of cubes, which is 13. So number of cubes. And we'll have to subtract out this middle section right over here. Let me do this. So subtract out the middle section right over here. So minus 5. So this is the number of yellow cubes. It feels weird to write the word yellow and green. The number of yellow cubes. Or another way to think about it, and you could just do this math right here. 12 plus 13 minus 5 is what? It's 20, right? Did I do that right? 12 minus, yep, it's 20. So that's one way you just get this is equal to 20 over 29. But the more interesting thing than even the answer of the probability of getting that is expressing this in terms of the other probabilities that we figured out earlier in the video. So let's think about this a little bit. We can rewrite this fraction right over here. We can rewrite this as 12 over 29 plus 13 over 29 minus 5 over 29 minus 5 over 29. And this was the number of yellow over the total possibilities. So this right over here was the probability of getting a yellow. This right over here was the number of cubes over the total possibilities. So this is plus the probability of getting a cube. The probability of getting a cube. And this right over here was the number of yellow cubes over the total possibilities. So this right over here was minus the probability of yellow and a cube. I'm going to write that way. Minus the probability of yellow. I'll write yellow and getting a cube. And so what we've just done here, and you could play with the numbers I just use as an example right here to make things a little bit concrete, but you can see this is a generalizable thing. If we have the probability of one condition or another condition, so let me rewrite it. The probability, and I'll just write it a little bit more generally here. This gives us an interesting idea. The probability of getting one condition of an object being a member of set A or a member of set B is equal to the probability that it is a member of set A plus the probability that it is a member of set B minus the probability that it is a member of both. minus the probability that is a member of both. This is a really useful result. I think sometimes it's called like the addition rule of probability, but I want to show you this completely common sense thing. The reason why you can't just add these two probabilities is because they might have some overlap. There's a probability of getting both. And if you just added both of these, you would be double counting that overlap, which we've already seen earlier in this video. So you have to subtract one version of the overlap out so you are not double counting it. And I'll throw one other idea out. Sometimes you have possibilities that have no overlap. So let's say this is a set of all possibilities. This is a set of all possibilities. And let's say this is a set that meets condition A. Let's say this is a set that meets condition A, and let me do this in a different color. And let's say that this is the set that meets condition B. So in this situation, there's no overlap. There's no way, nothing is a member of both set A and B. So in this situation, the probability of A and B is 0. There is no overlap. And these type of conditions, or these two events, are called mutually exclusive. Mutually exclusive. So if events are mutually exclusive, that means that they both cannot happen at the same time. There's no event that meets both of these conditions. And if things are mutually exclusive, then you can say the probability of A or B is the probability of A plus B, because this thing is 0. But if things are not mutually exclusive, you would have to subtract out the overlap. And probably the best way to think about it is to just always realize that you have to subtract out the overlap. And obviously, if something is mutually exclusive, the probability of getting A and B is going to be 0. Is the probability of A plus B, because this thing is 0. But if things are not mutually exclusive, you would have to subtract out the overlap. And probably the best way to think about it is to just always realize that you have to subtract out the overlap. And obviously, if something is mutually exclusive, the probability of getting A and B is going to be 0.